something a little different. We go around the room and ask people to come up with a possible rational root. If either you don't feel comfortable answering, or you don't know, or you weren't here, you can just say pass and go on to someone else. The polynomial we're looking at is 2x cubed plus x squared minus 13x plus 6. Exactly, section 3-4 on polynomial real roots. Where we start far back and again, trying to comfortable. So when we look at math, you have, when you think of like possible rational root, that we know using the rational root theorem for this polynomial.
I'm going to say pass on this one.
You get a pass? Okay. Armand, you want to try? Just one. Remember, this doesn't have to be a real, actual root. Oh. It just has to be a possible rational root that we would know from the rational root theorem.
I'll go pass. Pass.
Pass, okay. All right, Sue? Okay. Varun?
I'm going to pass on that. I'm going to pass on that.
Okay.
Yeah, I don't know.
Okay, that's fine. Next row, that's Macy. 1. I'm going to give a little away. I'm going to write it this way. Okay, thank you. Emma, do you know another possible rational root?
2. 2 over 1.
You're going to have to speak up because there's a lot.
2 over 1.
2 over 1. Okay. Nora, do you? 3 over 1. We'll discuss where these come from soon. Dorian? Okay. You can also tell me we're done. There aren't any more. You would be wrong right now. Jose?
I'm not sure.
Okay. That's a pass.
-6. -6.
Most definitely. Okay, where are we? Daily?
Okay.
Okay, good. Ezekiel? Yes, Victor? Chloe? You say half. I'm sorry, I'm just not here.
Pass, I don't know.
Pass, okay. Okay. Christopher?
0.
Again.
0.
No. You can see, well, I mean, It's not a root, is the question. A lot of these are roots, but see that 36. No. That's not a possible rational root.
4.
Sorry. So you got chosen late, so the easy ones were taken. Okay. I'm gonna thank you. I'm gonna do it that way.
Also, I can't see anything. There's a glare.
Can't have that. Feel free, anyone, anytime you have a problem like that, just, either ask me or take care of it. Yes? Yes. Excellent. I can't hear you over the jet engine. Yes. Okay, so we've got a good number. 1, 2, 3, 4, 5, 6, 7. You're new to San Francisco. This is a annual or semi-annual event where we get dive bombed. Cats scatter, terror. Okay, so let me just point out that assuming these are rational roots, always get both the positive and the negative. So how do we come up with these? Well, there are two numbers in this polynomial of importance. And this is only important if it's not 1. So this number has factors. Times 1. This number has 4 factors. So we take every combination of these factors and combine it with every combination of these factors. So there are a lot of them. Now, let's see, what are we missing? We got, I'm going to rewrite them because I think it's easier. And what's the other option? 2. Well, 2 over 2 is just 1, so I don't have to repeat that. 6 over 2 is 3. So okay, so we got 2, 4, 6, 12. Now, if there's no other way to factor this, you can go through this list. You can say, let's try them all, see if any of them are factors. let's give that a shot. Let's be optimistic. Let's start with 1. So e of 1 is 2 plus 1 minus 13 plus 6. No. Minus 4. That didn't work. This could be a lot of work. We might not find any. Let's try here 2. So that's 16 plus 4 minus 26 plus 6. 26 minus 24. You got one. From the remainder theorem, we know that if p of 2 equals 0, then x minus 2 is a factor. And so we can divide and simplify. So let's do that. I learned long division in high school. They didn't teach synthetic. It's more of a challenge. You're right this way. Synthetic. 2 times 2 is 4. 5. 2 times 5 is 10. Minus 3. 2 times minus 3 is minus 6. 0, which is what we better get. So now we know that polynomial, we know that we have one root, 2. And the polynomial is reduced now. We have p of x equals x minus 2. And we read off the coefficients here times 2x squared plus 5x minus 3. Well, this is a quadratic. I mean, either we're going to be able to factor it easy, or we can use the quadratic formula to find roots. So let's see. 2x, x, and I have to figure out where the 3 goes and the 1 goes. Well, it's negative, so one of these is positive, one of them is negative. I don't know that either. Your marketing tax dollars at work. Those vehicles, they drink about a gallon a second, something crazy. Maybe not that bad. Okay, looks like 3 and 1. If I make this plus and this minus, I get 5x. So that tells me my other 2 roots are going to be 1/2 and negative. So here we have a polynomial that, we don't really, there's a formula somewhere on the internet that will tell you how to just use the coefficients, but it's really hard to use. Here we have another option. So that's it. That's how we use the rational root theorem. Any questions? Well, I guess now's a good segue. I was going to say, you might find a problem like that on the next midterm. Next midterm is a week from yesterday. I'm going to put up another guide, things you need to know, but in general, it's first part of the year, first part of the semester, and polynomials. We're going to stop whatever we finish up today. That's what could be on the exam, but or maybe a little on the exam. But polynomials, the next sections won't be on the exam. And I'm going to try and come up with some example problems for you to practice on. Yes.
So you said the midterm is when again?
So basically, so 2 days ago was Tuesday, and 2 weeks from then. No, wait, I'm sorry, I'm wrong, that's break. It's the Thursday after that. It's the Thursday after you come back from break. So 20th.
Oh, 2 weeks.
Okay. Complex zeros and the fundamental theorem of algebra. Algebra. That sounds pretty important, doesn't it? We don't run into that many fundamental theorems. Does anyone happen to recall the fundamental theorem of arithmetic? We've all done arithmetic. Anyone know what the fundamental theorem is? They might have passed over that. It's something you sort of know, but maybe you haven't heard it this way. It's like if I have some number like 12, and I want to break it down into prime numbers. So that's like 2 times 6, 2 times 3. Okay, I'm done. So that's 2 squared times 3 to the first. Fundamental theorem says any integer, or a natural number, can only be broken down one way, into primes. So, important theorem. Fundamental theorem of algebra, it doesn't sound that impressive when you first hear it. It says, every polynomial equation has a complex root. Now, I want to make clear when it's just a complex root, complex numbers a plus bi, where a and b are real numbers, but you can have b 0, right? So all real numbers are complex. So polynomial equation might have a real root, but at the very least it has a root that's complex. Now, we're not going to prove this. It's not for lack of, well, there's lack of time. It can take about 2 years to prove it. It doesn't have to take 2 years for proof, but before you can see the proof, you have to have taken an upper level math course called real analysis, followed by an upper level course called complex analysis, where they prove this. It's a very, very deep and interesting theorem of proof. And it does something that happens a lot in mathematics, which is you have something to prove in one area of mathematics, and you end up like people spend years looking for an answer, and then they move off into another area of mathematics and they find it. And so the area we have to look at is complex analysis and maybe some number theory too. So we don't have to worry about it. We just know for this class every polynomial equation has a complex root. That is, there's some C, remember the complex numbers, which P of C equals 0. Well, there's a little more we can do with this now. We have this theorem. Because we know that P of C equals 0, and x minus C is a factor. That is, P of x is equal to x minus C times some other polynomial. But we know from the fundamental theorem of algebra that this polynomial has a root. And furthermore, since we divided P of x by x minus C to get P of x, we lowered the degree by 1. So we can repeat this. P of x is equal to x minus, let's say, d times r of x. And we can keep doing this until we get to a linear equation, which we can solve. Ax plus b equals 0. The consequence of this is we now can say, starting with the fundamental theorem, we're not going to prove, but we can say without a doubt that P of x has n roots. So, second degree quadratic has 2 roots. Third degree, like we were showing before, has 3 roots. You just go right up the line. If I asked you on the exam, how many roots does this equation have? You shouldn't have to think very much, should you? You don't know what they are. Well, you might be able to find one. Might not. Okay, now you can find one if you're smart. But there are 105 of them. There's definitely 105 of them. Okay. This is called the complete factorization theorem. And for my money, if you want to call this the fundamental theorem, it's equivalent. It's one follows directly from the other. All right. Anybody need any more time for this? All right. So I'm going to repeat what we did in the first part of the class, because some things are worth repeating. How many roots will this have? Is that easy? Thank you. But we don't know what they are, and we don't know how to factor this right away. So, once again, we invoke the rational root theorem. This one's a little easier because we've got a 1 here. We try again. You want to tell me what the roots are? Possible rational roots? There's got to be a brave soul out there. Yes? 1, 2, and 4. However, let's not forget that these will be negative. And since this is just a cubic, just 3, once we reduce it down, once we divide, what's going to happen? We're going to have a quadratic. We know we can solve that pretty easily. So let's see. Once again, 1 minus 2. Oh, no. 1, 0 minus 2. And 4. Everybody see why I had to put a 0 in there? There's no x squared term, but there is. It's just 0. Minus 2. Again, doing synthetic division. Minus 2, minus 2, minus 2, minus 2, minus 4, minus 4, 0. Now we know that this reduces to minus 2x squared, minus 2x, minus 4 equals 0. Well, we're going to make that a lot nicer. X squared plus x plus 2 equals 0. This is not going to factor nicely, so I'm going to use the quadratic formula. No. No. 1 minus, it is. Did I get the wrong answer here? No. Once again, minor error occurred. We'll try this again on hand. It's as well. X cubed plus 0x squared plus 2x plus 4. Divided by, well, if the root is minus 2, what's the factor? X plus 2. X squared, x cubed, plus 2x squared, minus 2x squared, plus 2x, minus 2x, minus 2x squared, minus 4x. student out there and can see what's going on. Oh. Copying error. That explains a lot. All right, x squared minus 2x plus 2. Let's do quadratic formula. 4 plus or minus square root of 4 minus 8 over 2. All right. Two plus or minus I. I think I got that right. Okay, so I want to factor, well, if I just want the roots, I have them. If I want to factor x plus 2 times x minus 2 plus I times x minus 2 minus I. Factoring the polynomial using fundamental theorem and the rational root. All right. We're almost done with all our factoring tricks. Before I go on, any questions about this? I mean, obviously you need to practice this on homework, and you need to be able to do this. Find the roots. There's one more strategy that it's a little simpler than this, if it works. And it's one of those things like the a squared minus b squared, where you just have to kind of sniff it out. You see it? The technique is factoring by grouping. And I'm going to give you an example here. This is a polynomial that we can apply this to. Now, they're more complicated versions, but what they're going to all have in common is they're going to have an even number of terms. They might have something missing, but if they have it missing, it's going to be each group is going to be missing a term. So if like there's 0x squared here, you'll see a 0, on something else. So the idea is you can group this. Either you can group it into groups of 2 or 3. You think ahead a little to what it looks like it's going to work. But you group it into pieces, and then you say, let's factor each of these individually and cross our fingers. So here, I look x cubed minus 3x squared. What are the common factors? X squared. And what have I got here? Well, I just have x minus 3. quadratic. I can't factor it in reals. You might recognize this form, x squared plus a positive. You can. X squared minus something. You can always do a squared minus b squared. There's a name for this. We call this irreducible. On the reals. And, here again, our roots, obviously 3. The roots here are I and negative I. So that's polynomial, that's factoring by grouping. If I put something like this on the exam, I'd probably tell you. Factor this by grouping. But in the real world, you might have to kind of see it yourself. All right. I want to look at something called, we've seen this a couple days ago, but in a different context. This is multiplicity of zeros. So let's look at, just for a second, this polynomial equation. Christopher, how many roots does this polynomial equation have? Just 5, absolutely. Well, I mean, you might have to kind of think, well, if I multiply this out, what's the biggest degree? It's going to be 5. And we already, the theorem tells us they're 5. So what are those roots? Well, there's obviously 1. And then there's 1 and 1 and 1. They're all 1. I mean, that theorem doesn't say they're unique roots, it just says there are 5 of them. So we call this multiplicity 5. You can have that. Just to tie in, if you're graphing a function, if the multiplicity is even, like in y equals x squared, your graph is not going to cross the x-axis, it's just going to have a point on it. It's even. If it's odd, like this is going to go through 1. If it's odd, it's going to go through that point. All right. Some kind of example here. Well, let's just say we wish to factor x equals well, we don't have something nice like a quadratic. But if you recall the other day, I mentioned this idea So you can look at these things here, these multiplied by as themselves functions. We can think of this as x squared plus 8x squared plus 16. And we can solve for x squared. Which, if you look at this closely, it looks like a nice pattern, right? You got something squared, and 2 times those 2 things here. That's a plus b quantity squared. So we have x squared plus 4 squared x 0. All right, well, try and factor that. Again, not reals. Right? That's x plus 2i, x plus x minus 2i. It's a conjugate where you end up x squared plus 4. But that's squared, right? So it's x plus 2i, x squared. What did I just write there? Yeah. X plus 2i and x minus 2i, and we have 3x. Okay, now we're in a good place to find all our roots. This tells me 0 is a root. This tells me negative 2i is a root. This tells me 2i is a root. This tells me negative 2i. I'm just going to make up some notation. There's 2 of them. And this tells me we've got 2 of these. So we've got 0 is a root, negative 2i with multiplicity 2. We've got 2i with multiplicity 2. We have our 5 roots. We found them all. Having done all this work, we're now going to try and reverse what we've been doing. Let's say I have some polynomial, and I know its roots. Let's just say they are 1, 2, 3. What's a polynomial? What's a polynomial that has these roots? How can I construct that? Well, you know, it has factors x minus 1, x minus 2, x minus 3. Each of these roots will make it 0. There is a little flexibility here. We could have some constants. Let's call it a. So, without some additional information, I can't really tie it down to one specific polynomial. But I might have some information. What if I happen to know that E4 equals 12? Right, so that's A times what? 3? 3 times 2 times 1. Oh, 12. So 6a equals 12, and now I can find that my a is 2. Just what you can do with another piece of information. All right. Let me go back to complex numbers for a second. You may recall that you have some complex number and you multiply it by a minus a plus pi. You multiply it by a minus pi, its conjugate, you end up with a real. So this, of course, is equal to a squared minus b squared I squared, but I squared is just minus 1, so this is just a squared minus b squared. So if I told you I had a polynomial, and one of its factors is 1 plus I, and I told you it has real coefficients, you can kind of guess already what another one of the factors has to be. To get rid of this complex or imaginary component, you're going to have 1 minus I. I'm sorry. And X. All right, that's just a feature of conjugates. All right, we'll stop for a break for 5 minutes. It's a polynomial with roots 1/2 and 3 minus I. And I want it to have real coefficients. So I'm going to need another root. So what does that other root have to be? Yes,
Would it just be 1 over 1?
let's see. X minus a half, x minus 3 minus I, x plus 1. Oh, wait a minute. It's not going to go away, is it? In fact, you can see already the constant term is going to be the product of these constants. So it'll be 1/2 times your 1 times 3 minus I. So it's going to have a complex coefficient, which is what we want to get rid of. How are we going to get rid of that? I'm just going to call this 2x minus 1. That'll give me a root of a half. X minus 3 minus I times x minus 3 plus I. All right, let's multiply these two together and see what happens. So that's x squared. That's the first. I'm just foiling, these guys. X times 3 minus I times x times 3 plus I plus 3 minus I times 3 plus I. Okay. What happens here? X squared plus 3x minus I times x plus 3x plus I times x over here. And now I have to do this multiplication. Well, this is a minus b times a plus b. A squared minus b squared. So 9 minus I squared, which is minus 1. So it's just 10. The minus ix and the plus ix go away. We end up with x squared plus 3x plus 10. So we accomplished just what we wanted. These three are roots. Wait a minute. What did I do wrong here? Oh, I didn't do this. Thank you.
Can it be 6x? 6x?
Yes, thank you. Finally, people are paying attention. Oh, I'm sure you're all paying attention. Okay, that's kind of it for polynomials, although things we learned about, things we've learned about polynomials will come up a lot in the next section. You better rev up the computer here. So we want to look at some graphs. Okay. So our next section is 3-6, which is rational functions. You may recall the rational expression has the form p of x over q of x. So we can make that into a function where p and q are polynomials. Note that wherever q of x is equal to 0, the function is going to be undefined. So that won't be part of the domain. A rational function can look somewhat like a polynomial function. Its graph can look similar, but there are going to be some differences. And to evaluate these kinds of functions, we're going to look at some features of these functions. The first one we talked about for polynomials is the end behavior. You recall that's what does the function do when you get very, very negative, or you get very, very positive. The second thing we're going to look at is something called a horizontal asymptote. I hope you have some familiarity with asymptotes. We'll go over what they are. And likewise, vertical asymptotes with S. We're going to look at the zeros, or if you like, the roots. You can also think of these as the x-intercept. Where the function crosses the x-axis. And finally, you can look at the y-intercept. You probably recall from our working with lines that if you have a linear equation like this, that b is where the line crosses the y-axis. For a more general function, well, there's going to be some place where that happens. It's not going to be a line necessarily. All right. Let's start with end behavior. It's a little more complicated than for a polynomial. So we're going to look at 3 cases. The first case is something like this function. This is x to the 5th plus 1 over x squared minus 1. I think, oh wait. This is some function. What happens when x gets very large? Well, x to the 5th, this portion, this term dominates, and the 1 becomes kind of irrelevant. Down here, as x gets very large, the minus 1 gets irrelevant. So what happens is this tends towards x to the 5th over x squared or x cubed, the end behavior. So what do we know about the end behavior of x cubed? Well, it kind of goes off to the stratosphere as you get larger, and as you get smaller, it goes down. All right, so let's take a look at a graph of that. So let's first just look at x cubed, see what that looks like. All right. Should be familiar with this. Off to the right, it's going to go straight up, and off to the left, it's going to go straight down. So let's look at our function now. X to the 5th. So if you look at the red and the blue lines, so you go off to the right, you see they kind of merge. So you go off to the left, they also merge. It's just what happens in between is different. But again, we're looking at the end behavior right now. So that's the first case. The polynomial, the p, has a larger degree than the smaller polynomial. And what we're finding is the end behavior is similar to a polynomial whose degree is the difference. So that's the first case. Call that case 1. Case 2, well, here's our example. I'm going to say 2x squared plus 4 or x squared minus 4. Well, here again, as x gets large, it's going to dominate. In this case, we have 2x squared. This 4 is going to become kind of irrelevant. But in the denominator, x squared is going to dominate over the minus 4. So this is going to start to look like 2x squared over x squared, and it just looks like 2. Well, again, let's take a look at that. There we go. All right, what's happening out on our end behavior here? The function gets closer and closer to 2. That's our end behavior. It actually never reaches 2, does it? So when you have a function that's doing kind of a soft landing, it gets closer and closer, but it never reaches. That's what we call a horizontal asymptote. Turn this off again here. So here we're looking at the second case where the degree of both polynomials is the same, you're going to get a horizontal asymptote. And you can figure out what it is pretty easily. You just divide the coefficients on the largest term, the leading coefficients, and you can see that these, this function is going to be asymptotic to the number 2. I think it should be obvious what the next example is going to be, case 3. It's going to be, well, our example is going to be 2x plus 4 over, we're going to do x cubed minus 8. Okay, so again, as x gets large, the 4 becomes irrelevant. As x cubed gets large, the 8 becomes irrelevant. So this is going to go to 2x over x cubed, which is going to go to 2 over x squared. 2 over x squared happy. Let's take a look at both of those. And we have to wait for it to warm up. Okay, so this is 2 over x squared. You'll notice as we get close to 0, both, as we move inward, well, let me back up. We've been talking about end behavior. As x gets very large, this is going to get close to 0 in either direction. Since it's squared, it's going to be coming always from the top. So you see, of course, the end behavior here is again to be asymptotic, horizontally asymptotic to 0. But also note that as we get close to 0, the function is shooting up. Right? Wherever you get a 0 in the denominator, you're going to get a vertical asymptote. That is, as close as you get to that value x, in this case 0, the larger or the further negative it's going to become. All right. What happens with this function? Well, for starters, it does get asymptotically close to 0. Why does it not do it from the same side? I typed it in wrong. I confused myself. Well, obviously, that's the way it is. I'll have to think about that. I'm just wondering if x is negative and x cubed is negative, shouldn't their difference be? I can see why. Okay, you're not wrong. You're just not looking close enough. If you zoom in, you'll notice, in fact, here we cross back over the x-axis, and we are coming from above here. All right. So, as I was thinking it should, as it does, is asymptotic to 0 from above, just like 2 over x squared. But there's some more features here. You'll notice this function, x cubed minus 8, well, if we factor that, one of the factors is going to be x minus 2. It's going to be 0, so we have, again, a vertical asymptote. Also, 2x plus 4 is going to have a 0 at minus 2. So this is kind of showing most of the features that we're going to run into with rational functions. Horizontal asymptotes, vertical asymptotes, zeros. So again, these are features you're going to run into if you look at the graph or you investigate a rational function. All right, while we have this up, we're going to look at another function. For example, it's kind of a contrived example, but this is a polynomial with zeros at 1, 2, 3, and 4. Not typing in the right place. And the denominator is x plus 3, x minus 4. Okay, so lower this up a little bit. All right, so what do we see here? As expected, there are zeros at 1, 2, oh, wait a minute, typo. There we go. We see the function crossing the x-axis at 1, 2, and 3. It's not crossing the x-axis at 4. Something happened there. In fact, if you think about this function at 4, it's undefined. But it does, at least on decimals, it seems to be going through there smoothly. Decimals is pretty smart. And if you go over with your cursor, and you get right on here, you can see he knows it's undefined, but careful. Right? So, when you have a function like this, well, the first thing is, if you have a factor like this, of course the function isn't defined there, but the function's also going to look as if it wasn't there at all, except at that one spot where it's undefined. This is 1 everywhere, except at 4. So this is another feature of polynomials. When you're evaluating them, as long as you don't forget that the function is not defined at 4, it's not in this domain, you can cancel that and evaluate it. Topic we're going to talk about with respect to rational functions that we've already talked about in a more general case, which is point of 1. We were to transform it this way. How's that going to transform it? Well, the vertex is going to move over, each point is going to move over to the right one. Same thing applies to all functions, and in particular, rational functions. So, one might be able to take advantage of this in the following manner. Let's say we have a function 2x plus 3 over x plus 1. And we want to rewrite this. We're going to divide 2x plus 3 by x plus 1. 2x plus 2, remainder 1, or 1 over x plus 1. I guess I'm going to write it this way. X minus 1. Y minus 2. So what you might expect is, if I were to instead just look at the function y equals 1 over x,